For section 4's chapter 10, section 4's notes, changes of state. I'm going to do in 3 parts so it all fits, and I'll mention this in class. Anyway, the first part, as you can see here, section 4, changes of state. What we're talking about is going from a solid to a liquid to a gas, and then maybe back down. You can probably understand and appreciate that if I'm ever going to go from a solid to a liquid and a liquid to a gas, I need to add in energy in order to do that. And consequently, if I'm ever going to go the opposite, from a gas to a liquid and a liquid to a solid, I'm going to be taking out energy, or energy somehow has to be removed. Okay, let's go to the first slide. A change of state. Again, a change of state is going from a solid to a liquid to a gas, or it could be going from, like I said, reverse, or you could be going from a solid all the way up to a gas, or a gas back down to a solid. So those are all changes of state. First question, what conditions are necessary for evaporation to occur? So if I have liquid water and that has to evaporate to become a gas, it has to, again, take in energy, and the attractive forces from one water molecule to another, those have to be overcome. And those attractions are pretty strong, and the energy that it takes to strip away those bonds or to overcome those forces of attraction comes from the energy absorbed from the outside. So it happens at a decent rate where you can observe it over a couple days, but you can't notice it as you're looking at it over a few minutes. So again, 2 things that need to occur: enough energy has to be absorbed, and that energy absorbed overcomes the attractive forces of those water molecules. So here we have this next question right here. What conditions are necessary for condensation to occur? Again, it's the opposite. Condensation is when gaseous water vapor becomes liquid. So that water vapor has more energy, the gas has more energy than the liquid. So the energy has to be somehow taken away in order for the vapor to form as a liquid on the outside of, let's say, a cold can of pop in the summertime. So as it says right here, you need a loss of kinetic energy, and that's usually through temperature. Okay, it could be through just movement. Next, all right, changes of state and equilibrium. Okay, a phase, of course, let's look at that. It's a part of a system with uniform composition and properties. So you have the solid phase. All the particles are in the solid phase. They're bonded relatively close together. You have the liquid phase where all the particles are relatively close, but they can move. And then you have the gas phase where the particles are very far apart, and they're very, very dynamic. So now let's take a look at equilibrium. Now I've highlighted a couple, at least put in italics, a couple phrases here. You read there, it's a dynamic condition in which 2 opposing conditions occur at equal rates in a closed system. Let's take a look at the first thing, which is a closed system. It's actually the last thing. I got to have a cap on it. So picture a 2-liter bottle. So I've put the cap on the 2-liter bottle. Now the next couple things you won't be able to notice. So I put the cap on the 2-liter bottle. If I'm saying it's in equilibrium, what I'm saying is that 2 opposing forces, or 2 opposing conditions. So in my bottle, I have water. And in this water, okay, here's the water, I have evaporation, and then I have condensation. Those are the 2 opposing conditions. And next, they occur at equal rates. So evaporation is occurring just as fast or just as frequent as condensation. And the last point, a dynamic condition, it's always happening. It's cyclical. It's always happening. It never stays or never becomes static. Okay, so that's something that's in equilibrium. And this is just an example of evaporation versus condensation. Next, equilibrium vapor pressure. It's the pressure exerted by a vapor in equilibrium with its corresponding liquid at a given temperature. Okay, so if I have an equilibrium, I better have every single one of these points here. But now an equilibrium vapor pressure says that if this is my 2-liter bottle with the cap on it, there's going to be particles up here. And that's going to force a pressure against the sides of the container and on the surface of the liquid. Okay, what we're saying is that's an equilibrium. In other words, the 2 opposing forces is that the condensation versus evaporation are happening at equal rates. Okay, but now the important thing that we need to keep in mind is at a given temperature. So if it's at a given temperature, it's pretty cold in this room right now. Let's say at a given temperature of 20 degrees Celsius, water is exerting a vapor pressure at 20 degrees Celsius. If I increase the temperature to 25 degrees Celsius, it's now no longer in equilibrium. Time has to pass by. If the temperature gets hotter, you will notice that there will be more evaporation and less condensation. If that's the case, then what's going to happen is that time has to pass by to where the temperature will get to where this system will adjust to this temperature, and the two will eventually become equal again. So it says here what happens when temperature is increased in this question here. The kinetic energy of the particles increase, vapor pressure increases, and equilibrium vapor pressure is established at a higher temperature. So if I change the temperature, it's no longer in equilibrium until it adjusts itself and becomes back in equilibrium again. Here's some pictures. Equilibrium vapor pressure / evaporation in a closed system. So notice this system is open right here. And you'll notice that you have just as much evaporation as you do you have more evaporation than condensation. Why is that happening? Because the particles keep escaping out the top. Now in this one over here on the right side, you have just as much evaporation as condensation. You do not have a cap. You have a cap and you have the parts that are in the same, they are in equilibrium, two opposing forces in a closed system, very dynamic. All right, next. And I'll probably end this first portion here. Changes of state and equilibrium. Here you have vapor pressure and equilibrium vapor pressure are specific to a liquid, and that makes sense. Everything evaporates at a different rate. Alcohol evaporates at a different rate than water, and alcohol is faster than water, and water evaporates faster than, let's say, crude oil, and so on. So I could pick any liquid, and they all have different vapor pressures and equilibrium vapor pressures. The question is why? And this point right here is they all attract each other. The molecules attract each other with forces that are different. Alcohol attracts another alcohol molecule weaker than water does water, and that is even weaker than, let's say, crude oil to crude oil. So the weaker the attractive forces, the higher the vapor pressure. Now that's what I said here, right here. Weak attractions equals a high vapor pressure. Why? Because they're evaporating very quickly, because they only have weak attractions holding them together. However, if you have something like molasses or syrup or something like that, which has very strong attractions, it's real thick, it's real goopy, that equals a very low vapor pressure because we have very strong attractions. Okay? Now, another word that pops up here under weak attractions is something called a volatile liquid. A volatile liquid is not how explosive it is, it's how fast or how readily it evaporates. Okay? So vapor pressure and equilibrium vapor pressure is dependent upon the attractions between molecules. We call those the intermolecular forces. Okay, that's the end of part one. I will upload part two.